Connections make a material. Look at steel. It is an ideal structural material because it is easy and simple to connect. But equally, if the wrong connections were chosen, the structure might be difficult to build, might not function properly, and might be completely uneconomic. Standard components, such as steel plates, universal beams, channels, angles, and hollow sections, all need connections to turn them into efficient structures. A connection needs adequate tolerance, so that it can be easily assembled on site, adequate accuracy, so that it all fits together and the final structure is the right shape and size, and adequate space for nuts and bolts, including space for the spanner or impact wrench to tighten the nuts. Adequate space is also required for welding. In this connection, for example, it is not possible to weld along the end of the angle lug. It is important to distinguish between work which can be done on site and work which can be done in a fabrication shop. In a fabrication shop, there are large automatic welding machines available. It is possible to move large pieces, turn them over, and weld downhand. Jigs can be used to clamp pieces for welding, and there are testing and inspection facilities on hand. In contrast, on a site, connections may have to be fixed far above ground. The weather may be inclement, and the piece of steelwork may only be supported by a crane while the connection is made. So, in general, we can say, connections on site should be bolted, whereas connections in a fabrication shop should be welded. Now, what about transport? Ideally, the structure should be brought to site in a number of convenient pieces, which are easy to connect together. Because site work tends to be more expensive and less efficient than work in a fabrication shop, the pieces should be as large as possible, and yet not too large for convenient transport. Transport limits are generally governed by size rather than weight, but remember that the piece has to be offloaded and often stored on site before being erected. Ideally, the choice of connections should allow separate pieces to stack conveniently and efficiently while being transported to site and stockpiled. Connections should also be designed to minimize damage from mishandling. In other words, cleats and plates which stick out from the member should be avoided as far as possible. A connection must transfer load right the way through the connection. In this bolted tension connection, the tensile load must pass from one member through the weld to the end, through the weld, through the bolts, through the weld, to the other end, and through the weld into the other member. There must be a continuous load path through the connection. A single weak link in the load path will cause failure. However, sometimes it is desirable to limit the magnitude or type of load transmitted by a connection. This can be achieved through the choice of connection. In this example, let's suppose that the connection to the base is relatively rigid. When a load is applied, a moment, as well as the horizontal and vertical forces, will be transmitted to the base. This leads to high peak bearing pressures, which would be undesirable if the ground conditions were poor. It would lead to failure or necessitate a large and more expensive foundation. But in this example, the connection at the base can accommodate a high degree of rotation. This significantly reduces the magnitude of the moment and produces almost uniform bearing pressures, which are less than the high peak bearing pressures obtained when the base column connection was relatively rigid. Similarly, a beam column connection can be designed so that when a load is applied to the beam transmits a moment into the column as well as the vertical load. Alternatively, the beam column connection can be designed so that the beam transmits only a vertical load to the columns. The cost of erected steelwork can be broken down into the following elements: material, fabrication, protective treatment, transport, erection. Typically, the proportion of the total cost might be material, 25%, fabrication, 30%, protective treatment, 20%, transport, 10%, erection, 15%. But these figures may vary tremendously from one type of steelwork to another. Poor connection design can easily double the cost of fabrication, transport, and erection. It can affect the quantity of material and thus the cost of protective treatment. So good connection design is vitally important in the production of economic steelwork. Let's summarize. We've said that connections enable steelwork to be used to its full potential. To do this, connections must carry the load required. They should distribute the load where desired. They should be easy to fabricate. They should divide the structure into sections which are easy to transport and which are easy to assemble. If these conditions are achieved, the connections will be cost-effective, and they are likely to have more effect on the cost of the structure than a refinement in member design leading to a small saving in material. Now, for the rest of this program, we shall concentrate on the kind of connections typically made on site. These are bolted connections. Bolts can be loaded in tension, or they can be loaded in shear. This may be in single shear if one surface is sheared in failure, or in double shear if two surfaces are sheared. Treble or quadruple shear are possible, but are seldom used in practice. A bolt may also be loaded in a combination of tension and shear. When a bolt fails in tension, it will generally fail in the threads where the section is reduced. The ultimate tensile force in the bolt is equal to the ultimate tensile stress multiplied by the net area. When a bolt is loaded in shear, in this case in double shear, it can fail by shearing. When this happens, it is at a load approximately equal to the ultimate shear stress multiplied by the surface area sheared. Here it is the cross-section of the bolt multiplied by 2, as it is in double shear. Alternatively, it can fail by bearing of the bolt on one of the plates. Failure occurs at a load approximately equal to the bearing stress multiplied by the thickness of the plate multiplied by the diameter of the bolt. If the bolt is too close to the edge, it may tear out. At a load approximately equal to the ultimate shear stress multiplied by the area sheared. These are rather idealized simplifications of fairly complex behavior. However, the simplifications enable us to make a reasonably accurate prediction of failure loads. This enables us to design connections which are strong enough and yet not wastefully strong. In a typical connection, there is likely to be a variation in the load between one bolt and another. Conventional elastic theory indicates that the load in a bolt is proportional to the movement. Hence, when this simulated connection is loaded vertically and symmetrically, the displacement, and hence the load, is the same in each bolt. It is the same with a symmetrically sideways load. However, this eccentric load produces a combination of vertical and horizontal movements, and the load is distributed between the bolts according to the formula R over sigma R. However, for collapse, all the bolts must fail, although a mechanism is formed with the failure of all but one bolt. In this eccentric lap connection, the connection twists as the plates try to straighten out. The loading in the bolt changes from one of simple shear into a combination of shear and tension. Because of prying action, the load in a bolt can even be higher than the load on the connection. If we consider the forces, we can see why this is so. The load in the bolts can be greater than the load on the connection because of leverage about the point of contact. Even in the symmetrical case with 4 bolts, prying action can affect the loads in the bolts significantly. It is important to distinguish between strength and movement. In this connection, there is considerable movement as the load is applied. If greater strength is required, we could use more bolts, or larger bolts, or thicker plates. However, if less movement is required, then we could use close tolerance bolts or high-strength friction grip bolts. Alternatively, we could change the design of our connection. In this typical end connection of a beam to a column, the bottom cleat has been welded to the column, whereas the top cleat has been welded to the beam. As much of the work as possible has been completed in the fabrication shop, where welding facilities are available. On site, the beam can be swung in and landed on the bottom cleat. It can be positioned with a podger spanner and the connection quickly completed. Consider this connection under a vertical end shear. there is flexibility in both angle cleats, but particularly in the top cleat, where the slack in the holes has to be taken up. Hence, the shear forces pass through the lower cleat and into the column. In this end connection, a single web cleat has been used. The cleat has been welded to the column in the fabrication shop. Again, the connection can be quickly completed on site. Under the action of a vertical end shear force, there is considerable vertical movement until the slack is taken up in the bolt holes. The shear force is taken via the bolts into the shear cleat and through the weld into the column. Now, consider the same connections under the action of a bending moment. This connection produces little resistance to small rotations, as there is tolerance in the holes to be taken up in the bottom cleat. Even then, the angle cleats themselves are not very stiff. Note how the load path goes through the angle cleats. This connection is also very flexible and produces very little resistance to small rotations, again because of the tolerances. The plate cleat is also much less stiff than the beam. Note how the load path goes through the bolts in the cleat. In contrast, this connection is much stiffer and will therefore attract more moment through to the column. It may come close to a theoretical rigid connection between beam and column. Consider the relationship of the moment to the rotation of a connection. A perfectly frictionless pinned connection would be the horizontal axis, rotation without developing any moment. On the other hand, an absolutely rigid connection would be the vertical axis, no relative rotation between the beam and the column. But these are only theoretical possibilities. This connection is not frictionlessly pinned. And nor is this one. Nor is this one absolutely rigid. But for acceptably small amounts of rotation, it is reasonable to consider connections as being either pinned or rigid. The typical beam-column connection has, of course, to take a combination of both vertical shear force and an end moment. If desired, the size of the end moment can be kept very small by allowing the connection relative freedom to rotate. So, if the beam-to-column connections are like this, or like this, in this structure, only a very small moment is transmitted through the connections and into the column, and the bending moment is like this. The central bending moment in the beam is almost identical to that which would be obtained if the beam had been simply supported. It would behave very much like this. But suppose we had this connection. Then the bending moment would be like this. And this is how the structure would tend to behave. But suppose the beam is very much stiffer than the column. Then the beam-to-column connections will have very little effect, whether they are rigid or flexible. The beam is so stiff, and the column so flexible, that even with an absolutely rigid connection, little moment is attracted to the column. Compare it with this example, where the beam and column are of similar stiffness and rigidly connected. It is important to see a connection as much more than the bolts or the weld. Connections frequently lead to concentrations of load and consequent local overstressing. Stiffeners may be needed to prevent this. Otherwise there would be deformation, caused in this case by the concentration of forces in the beam flange. This connection would behave much more like a pin than a rigid connection because the end plate is so thin. So, the design of connections is vitally important. Connections will often determine the overall economics and practicality of the structure. The behavior of the connection under load will determine the behavior of the structure. Any weakness in the connection will be the weakness of the structure.